Alright, in this video we're going to begin talking about lipids. Specifically, in this first video we'll be discussing a type of lipid called a fatty acid. And so, a fatty acid is just a carboxylic acid with somewhere between 12 to 20 carbon atoms. And so that makes these much larger than typical carboxylic acids you've seen before in class. That they usually have an even number of carbon atoms. And that has to do with the way that they're synthesized by living organisms. That they're put together 2 carbons at a time, and so we end up with an even number of carbons at the end. That the way that we describe these fatty acids is that we say that they have a tail group and a head group. I'll try to color code this just because I can. And so this black portion of the molecule is described as the tail, and this red portion with the carboxylate group is described as the head. And so the tail group of the fatty acid is what contains our 12 to 20 carbon atoms. In this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 total carbon atoms in this molecule. And so I've drawn it a little wrong. I should have added 1 more carbon atom so we get an even number. So there. And the head group is the carboxylate group, which is the conjugate base of a carboxylic acid. And the reason that I've removed the proton to add this negative charge to that oxygen is because at physiological pH, which is around 7, this carboxylic acid group will be more likely to lose that proton and become a carboxylate group. So anyway, we classify different fatty acids by looking at their tail groups. Different fatty acids have different tails, and they can differ by the number of carbon atoms or the number of carbon-carbon double bonds within the tail. And so there are... And so one way to classify carboxyl or fatty acids is based on the number of double bonds that they have. And a saturated fatty acid will have 0 double bonds, whereas a mono unsaturated will have 1 double bond. And a poly unsaturated will have 2 or more double bonds in the tail group. And so there are and these different classes of different fatty acids will have different chemical and physical properties. We'll get into that here. We'll look at the melting points of different fatty acids. That in general, as the tail of the fatty acid becomes longer, the melting points become higher. And so if we look at, we'll look at a few different fatty acids here. We have lauric acid, myristic acid, palmitic acid, and stearic acid. And these are the common names of the fatty acids rather than the IUPAC names of the fatty acids. But the common names are what's usually used. So if we look at the number of carbons, then it's 12, 14, 16, and 18 carbons for these 4 fatty acids. So we can see that even number rule for the fatty acids again. If we look at the number of double bonds, well, for these 4 fatty acids, it's all 0. These are all saturated fatty acids because they have 0 double bonds. Now, finally, we'll look at the melting point. It's 43, 54, 62, and 69 degrees Celsius. So we can see that as the size of the fatty acid becomes larger, as we go from 12 carbons to 18 carbons, then the melting point becomes much higher. That we go up by about 10 degrees Celsius for every 2 carbons that we add to the tail group of the fatty acid. Now, unsaturated fatty acids typically have their double bonds will lower the melting points. And so now we'll look at some unsaturated fatty acids, and I'll draw those in blue. We have oleic acid, linoleic acid, and linolenic acid. And again, these all have 18 carbons, and so you would expect these to behave similarly to stearic acid based only on size. But if we look at the double bonds, they have 1, 2, and 3 double bonds. So we have oleic acid be our monounsaturated fatty acid, and then linoleic and linolenic acids would both be polyunsaturated fatty acids. And we'll look at those melting points at 13 degrees, -9 degrees, and -17 degrees. And so the melting points for our unsaturated fatty acids are much, much lower than they are for the saturated fatty acids. That even though oleic acid is a much larger fatty acid than lauric acid, it has a much lower melting point just because of this one double bond. And as we increase the number of double bonds, we push that melting point even further down. And the reason that our saturated fatty acids have higher melting points than our unsaturated fatty acids has to do with the London forces holding these molecules together. And so if we draw out these molecules, so I'll begin with drawing some saturated fatty acids. we can see that these molecules sort of stack together. That the fatty acid tails can pack tightly together because they form more or less a straight line. I mean, I know that it looks zigzag, but that's as straight as we can get these carbon-carbon single bonds because of their tetrahedral shape. And so they pack together like these markers would pack together in a very orderly way. And so they have a strong London forces that hold the molecules together, and so it takes a lot of heat in order to pull those molecules apart and to melt them. That's why they have high melting points. But if we look at our unsaturated fatty acids, then we'll use a linolenic acid for this. And we have these three double bonds. And in fatty acids, at least the naturally occurring fatty acids, these double bonds are almost always cis double bonds. And so they end up putting a kink into the carbon chain. And it bends the molecule. It makes it more like a J shape than a straight line. And so if we have two molecules instead of just one, they don't pack together as well as the saturated fatty acids do. That if we have several of these J-shaped fatty acids, then they can't clump together in the same way that saturated fatty acids can. The saturated fatty acids can clump together very efficiently. I won't draw the head groups on all of these, there are too many. But the London forces are much more able to hold together the saturated fatty acids than they are the unsaturated fatty acids. And so they have much lower melting points. And anyway, another feature of fatty acids is they tend to have very poor water solubility, because if we look at the hydrophobic group, then this entire fatty acid, the fatty acid tail group is very hydrophobic, and our head group, which is hydrophilic, though, it's too small to compensate for the very hydrophobic fatty acid tail. And so that they have very poor water solubility. But if we try dissolving them in a basic solution so that we deprotonate the carboxylic acid group, like I've shown here, then we'll improve the water solubility by making a negatively charged head group instead of the protonated neutral head group, if we still had that hydrogen atom on the fatty acid carboxylic acid group. And so by removing that proton in a basic solution with a pH above 7, we improve the water solubility of the fatty acids. But anyway, that's our introduction to lipids and fatty acids, and we'll cover other types of lipids and what we can do with these fatty acids later in other videos.